Our next speaker is Hanjun Dai, and he'll tell us about learning loop invariants for program verification.
Okay, thanks for the introduction. I'm Hanjun. This is a joint work with Xujie, Mukund, Meiyu, and Li. So program verification is about formally prove the correctness of a program. To achieve such a goal, typically one needs to apply a set of rules. While most of the rules can be deduced automatically, the while rule requires something called the looping invariant. And finding the looping invariant is equivalent to the halting problem. So in general, it is undecidable. So what is looping invariant? Given a program like this, which contains a single loop, the corresponding looping invariant is a logical rule that tells some properties about the variables. So this rule should satisfy three conditions, namely pre-invariant and post conditions. So basically, it says this rule should hold true before, during, and right after the loop. So fortunately, it is relatively easy to check whether the proposed loop invariant is correct or not using some automatic theorem provers such as these three. So it is quite natural to formulate it as a Bandit problem. The agent keeps proposing the loop invariant, and the checker tells whether the proposed one is correct or not. So one can see that positive reward is only received when you actually solve the problem. This is quite difficult for reinforcement learning algorithms because of the sparsity and the non-smoothness of the reward. Another interesting challenge is, suppose we have found the loop invariant for a set of programs. Can we gain some insights and find the answer for new programs faster? To solve the sparsity issue, let's take a closer look at the checker. So every time when the proposed solution is rejected, the checker will provide additional information that tells you why you are wrong by providing this counter example. So the counter example is an assignment of the variables. So as the interaction with the checker goes, one can collect a set of counter examples. Recall that the loop invariant should satisfy three conditions. So here we can collect three sets of counter examples. One way to use this rich feedback is to evaluate the proposed loop invariant against those counter examples. So using the fraction of the counter examples passed, you can interpolate the reward between 0 and 1 smoothly. And we'll only call the checker once the proposed loop invariant passed all the counter examples. This can further reduce the requirement of the Z3 calls. Okay, to solve the generalization issue, here we propose a graph representation module. So using the graph neural networks, one can get a transferable representation of the source code. Okay, this is like the overall framework of our proposed code to invariant. So in each step, the agent will propose a predicate, which is part of the solution. And in addition to the final smooth reward we just talked about, we also added the additional intermediate rewards to guarantee the proposed predicates are valid. So to evaluate our framework, we collect a set of, in total, 133 benchmark programs. So each program contains a single loop with arbitrarily nested if-else branches. So we first treat the code to invariant as an out-of-the-box solver. That means we associate a set of neural network parameters to each of the program instances. And we compare against a set of solvers from program language literature. In this figure, the green curve is ours. We can see that with a fewer number of these recalls, we can solve more instances. And we can also solve comparable number of instances within 1 hour time limit. And to gain a tiny step towards finding the generalizable solver, we add some confounding variables to get the permutation of the programs. That's how we can get the programs with the same underlying semantics. And in this limited setting, we can see that with proper pre-training, we can get a better sample complexity comparing solving from scratch. Okay, thanks everyone, and welcome to our poster this evening.
Our next paper is titled Deep